no? What do you think?
I'm ready, yes.
Already, perfect. Then, okay, let's start then.
Yeah. Yes, okay.
May I make an announcement, Elijah?
Sure, yes.
Yeah, unfortunately, I didn't record the first hour of your lecture today. I'm very sorry.
Oh no, that was my first lecture.
I forgot.
Ever.
So anyhow, you have your
there are the slides.
Yeah, I have the slides on your site. Okay.
Okay, so at least I didn't write on the board. That's one of the advantages.
Okay.
Okay. So you are recording this part?
Now it's okay. Yes.
Yeah. Okay.
Okay.
No problem. Yeah. So okay. So I keep going. So let me continue where we let off. So remember, we were talking about this persuasion theory of Aldo Delfino and how you can use that to compute one-point functions. So I already explained this part, but let's go back a little bit. So essentially, this gives us a prescription to compute the post-quench ground state or a post-quench state after a global quench. So it is important in this approach that the quench is global. And when we say global, it means that it affects a global parameter, like a coupling of the model. So, so that allows us to expand this post-quench state in terms of the pre-quench state in a perturbation theory on this quench parameter. So one of the limitations of this method, of course, is that the quench has to be small. So if you want to look at large quenches, probably this is not going to help, or maybe you have to do perturbation theory to a very high order. And that is also a problem because, unfortunately, this method has only ever been used for first order perturbation theory. And properly defining this expansion for higher orders is actually rather complicated. So there are some limitations, but at the same time, this is very general. As long as you have some action, functional, and some coupling that you're changing, you can use this. So we have seen that this post-quench state at first order perturbation theory depends on form factors of the field associated with this coupling that we are changing. Now, if we want to compute the expectation value of some other field, for example, a field I call O here in general, if I want to compute this expectation value, and for good measure, I want to normalize it by subtracting this constant bit, so some time independent bit. So I'm computing something that should be 0 for time 0, essentially. Turns out that at first order in perturbation theory, the kind of formula you get for this is this. So this was also written in the original paper of Aldo. And so that's what you get when you take that expansion of the post-quench ground state and you essentially sandwich an operator between these two expansions and take the leading contribution. So you get a formula that's a little bit similar to what I wrote in the previous page. So there's still a conservation of momentum. Total momentum is 0, so quasi-particle picture. But then you have, instead of a state that was left over in the previous page, now you have a sum over form factors of the two fields, sort of the perturbing field, the coupling field, and the operator you want to compute its one-point function, of which you want to compute the one-point function. And you have the time dependence here in this exponential. And of course, then you have higher order corrections in this delta lambda, in this small parameter. So this is something that was known before I ever worked in this kind of problem. And what attracted us to this is that, again, form factors are the building blocks. So there is a good hope that you can generalize these twist fields and hence compute entanglement in this way. And indeed, it's actually not difficult to do this, at least formally, because the only thing you have to do really is to replace the operator O by the twist field. The only thing that changes, literally, is the number of the field and a factor n in front, because as usual, you have n copies. But the copies are not mixing here because the other field is a field that lives, well, just on each copy separately. So you only have the n contributions of the n copies of this field phi. So that is the formula for the twist field. So this means that this is a method that allows you to compute the one-point function of the twist field at first order perturbation theory. And so the question is, will that tell us something about these time-dependent behaviors of entanglement that we saw in some of the pictures at the beginning? Turns out that it tells us something, okay? And I'm gonna show you, well, in a bit more detail what this expansion looks like. So, sorry, let me go back. So if we look at this formula, again, we have a sum of form factors. And as usual, it starts actually at 1 in this case. So the VEF has already been subtracted. And so the first contribution will come from 1 particle form factors, then 2, and so on. So same story as in the previous application I described. If you write those contributions a little bit more explicitly, you see that from the 1 particle form factor, again, because 1 particle form factors are theta independent, integration can be carried out. And what you get is actually a sum of particle types only, and you get cosines in time. So you have pure oscillations there. And then the 2 particle form factors will give some integral like this that looks pretty complicated, and then you will have more terms. Now, what's interesting about these terms is that you can analyze them, and of course you can compute them for different models if you know the form factors. And in a moment, I'm going to show you the results for a specific model. But what you find when you study this a little bit is that the 1 particle form factor term, what it gives you is undamped oscillations, obviously. So there is cosines, nothing else. So you have cosines involving the masses of the excitations. And that's the only time dependence. So this is an oscillation that is going to be there for all times. Now, you look at the 2 particle contribution, that is more complicated because it depends on these functions, these form factors. These form factors are complicated. But if you do a saddle point analysis and you just look at the leading contribution to this kind of integrals, you generally find that this gives you oscillations as well, but these are damped. So that will give you some sort of cosines and sines divided by time raised to some positive power. So these will be oscillations that will be visible for short times, but would disappear for large times. And then you could ask, okay, so what about the linear growth in time that we talked about at the beginning that was predicted? So what is this linear growth? Well, unfortunately, within this approach, this linear growth is nowhere to be seen in this first order perturbation theory. And what we believe from experience, from studying many models, is that this linear growth becomes observable, can be computed only if you can compute the next order of perturbation theory. And so this means that if you do only first order perturbation theory, you're going to see some effects, you're going to see some features of entanglement that are interesting, but you're not going to see actually the leading large time behavior. And so you should be a little bit careful when you analyze these results about the conclusions that you can draw. So the approach might lead us to miss this large time behavior. So this is an important detail to notice, but it also gives us detailed knowledge of subleading oscillatory behaviors, which can be missed by other approaches. And in that sense, this is an interesting way to try and understand these other behaviors of entanglement, which actually are the subject of quite a lot of discussion at the moment. So one important conclusion of all this is that if you have non-vanishing 1 particle form factors, then automatically you're going to have persistent oscillations. And this is something that actually has been observed also for other observables, not just for the entanglement. So this is interesting. There is an important change between having 1 particle form factors present and not having them in these behaviors. So just to show you an example, I showed you this theory I talked about at the beginning. So this is the theory I studied with my collaborators, Jacopo Vitti, Istvan Széchenyi, and Matej Lenches in last year, I think it was published this at the beginning of last year. And so we studied this model. Remember, this was a mass quench in a theory that has 8 stable particles, all with masses proportional to each other. A very interesting theory, by the way, that was studied by Samologikov originally. So in this theory, we can do this calculation. There are 1 particle form factors that are not 0. Therefore, if we do analytic calculation of this type, we just get oscillations with these 8 frequencies of these 8 masses. The interesting thing is comparing that to numerical results. So we can do also a simulation on a computer of this quantum spin chain you saw at the beginning, and we can check if the numerics actually agree with this prediction, or if, on the other hand, our prediction is really just a result of first order perturbation theory, but somehow it doesn't really survive scrutiny when you do numerics. It turns out that the numerics agree very well with the prediction, in particular with the prediction that there are undamped oscillations. And this is not entirely surprising because there's a previous work actually where people looked at other observables and they also saw, for similar reasons, that there were persisting oscillations, in particular order parameter, so 1-point function of magnetization. So here you have some pictures. These are the Renyi entropies, Renyi 3 and Renyi 4 in these pictures for two different quenches, two different changes of the magnetic field. Both are small quenches. And you see that the numerics, the dots, and the analytical prediction, which are the oscillations on top, they agree very, very well. And the only adjustment that has been made there actually is to shift the numeric, to shift the analytic result by a tiny amount. And that's just because, well, there are all these corrections we are neglecting in our analytic results. So you notice that when you try and fit. But otherwise, there is no fitting of the amplitude or frequency oscillations. This is really exact. One thing that one can do also is to do numerics and then do a Fourier transform of the numerics. And this is the von Neumann entropy, Fourier transform of it. And if these oscillations are present, we should see, well, resonances. We should see signatures of these frequencies. And indeed, we see that. So we see a large peak here, which is the mass of the lightest particle. And then there's a smaller peak, which is the mass of the second lightest particle. And then we have another peak down here, which is the third lightest. And we even have M4, I think, somewhere here, which is the fourth lightest particle. And then we even have combinations of the masses, which can also be explained in this form factor picture. What is interesting is not only that we see those masses very clearly in the numerics, but actually the height of these peaks is directly related to the coefficient in this expansion here. So the height of the peaks is essentially the one particle form factors, okay? It's the coefficient of the sign. And so what is quite beautiful is that by doing numerics on the chain, we are effectively measuring the value of these one particle form factors. And we see that the agreement is pretty good. So these are these dashed lines that touch each of the peaks, so the horizontal lines. So that means that the quantum field theory can be compared to the numerical results in the chain in the correct scaling limit, and that the agreement is pretty good in this case. Something interesting for this model is that actually you can do numerics for very large times if you want, which is this picture here, and you can do numerics for large quenches as well. So you can say, okay, we see this for small quenches, but does this behavior persist for large quenches and after a long time? Well, what you see after a long time actually is that there is some growth of entanglement. So you cannot really see any growth when you look at short times like here. But if you go to times that are large enough, you see that there is a tendency to grow. And this is actually also expected. In this model, there are some arguments as to why first there should be linear growth because it's been predicted to be so. But it's also known that this linear growth should be quite suppressed in this case. And indeed it is. So you really need to go to very large times to see this growth. But otherwise, you see that the oscillations are still there and they don't seem to be damped at all. So it looks like this oscillatory behavior, which is led by these one particle form factors, is very, very robust. And there's still some more work to do to understand whether this is really a result, I mean, almost a theorem. If you have one particle form factors, you will have persistent oscillations always. If that is a result, then a generic result, which I suspect it is, then it's an interesting one for entanglement. You will see other effects on top of this. So you see sort of a big oscillation on top of all these little ones. And actually the frequency of that can also be computed. And it's also related to some combination of masses of these particles. So in this theory, there are 8 particles, actually, as I said. I mean, in the Fourier transform, we only seem to see the first 4 just because the other 4 are a lot lighter and it turns, a lot heavier. And it turns out, for example, that the sum of the masses of the first 2 particles is kind of still smaller than the masses of the last 4, let's say. So this produces a peak that is a lot more visible in the spectrum. Okay, so this example hopefully gives you an idea of how this technique is of some use in the context of equilibrium dynamics, and could be, hopefully can be still extended further to understand that dynamics a little bit better and to understand effects that go beyond the linear growth of entanglement in this situation. So this is the last slide of this example. So if you have any questions about this, I'm happy to have them now or later, but feel free to write on the chat or speak. Otherwise, I will go to my final example. Okay, so I'll go to the final example then. All right, so the final thing I want to show, my example 3C, is a particular, well, actually this is not so much an application, so the application does exist, but I'm not going to show it to you very much at least. But it's something related to composite twist fields, which I mentioned a couple of times during my talk. So I thought of presenting this example simply because this is a result from some work I did years ago, which is actually, I think, not very well known because it has an application that is really, really very specialized. But I thought it was interesting because it connects to some of the ideas of the form factor program, and in particular to the question I raised when I talk about form factors, about whether form factor solutions are unique or not, and how do we know if we have all the solutions? How do we identify the solutions? So I'm gonna talk about a specific example, a specific theory, and about the question of operator identification in relation to twist fields. So I told you already that given a solution to the form factor equations, it is not entirely obvious all the time how we know which local field this solution corresponds to. In general, all local fields with the same twist properties satisfy the same form factor equations. So how do you know which is which? I mean, this is one big question. So there are several ways to find this out. There are constraints on the form factor asymptotics, and I talked to you, I introduced some of this to you in my lecture, and these will narrow down the possible solutions. So essentially the asymptotics for large rapidity usually tells you a lot about the form factor. Other constraints come from the spin of the operator. So if you're looking for operators of spin 0, you know the form factor depends only on rapidity differences. Symmetry is also constrained form factors. So if there is C2 symmetry, usually only the even particle or the odd particle form factors would be non-zero. One of the most useful ways you can check your form factors is something called the delta sum rule, which is something I've used many, many times in my work. And it's a result by Delfino, Simonetti, and Cardi from '96. So this is the same paper where they gave an explanation for the clustering momentum space of form factors. And in that same paper, they derived this very nice formula. And this nice formula, what it tells you is that there is a certain two-point function in quantum field theory that you can integrate. And if you can integrate it and compute that result of that integral, that should give you the conformal dimension of the operator O inside this two-point function. So in other words, this delta sum rule relates a quantity that is defined in the gap theory, in the massive regime, to a quantity which corresponds to the ultraviolet regime, to the mass going to zero regime. So this is a very powerful way to identifying operators. So suppose that I know the form factors of these two fields. I know the form factors of O, but I don't know what O is. Well, I could plug my form factors in that formula, compute that integral, and if I get a number, well, I'll get some number, and if that number corresponds to the conformal dimension of some field that is present in the underlying CFT, then it's very likely that this field O is the massive counterpart of that field. So this is something that is used very often, but in order to use it, well, you need to know the form factors of this theta. This is the stress energy tensor, and of O, and you need to have form factors such that they are, they have to be non-zero for the two operators at the same time. So if one of the operators only has even form factors and the other one only has the odd ones, then unfortunately the formula doesn't tell you anything. But in many cases, well, it is useful. It can tell you something. So this gives us a direct connection to the conformal field theory, which ties in with the, well, fundamental ideas of Samologikov that an integrable massive QFT is just a perturbation of conformal field theory. So, okay, so this is all about identification. So let's talk about branch point twist fields a little bit. So when we wrote this paper of 2008, we used the delta sum rule to identify, to check our form factors in two theories. And actually, the two theories that we studied, which was Ising and Cinch-Gordon, they both have an internal C2 symmetry. And for that reason, the twist field form factors, they're vanishing for odd particle numbers. Okay, so there's already a restriction there. So we could use the delta sum rule, and we could use a certain idea about what the simplest solution to the form factor equations is, which is the one I wrote for you last week. But in general, though, there can be other twist fields associated with the same cyclic permutation symmetry, which are different from T. So we're always talking about this twist field T, but the question is, can there be other twist fields that satisfy the same equations? That's what I'm trying to say. If there are, well, they should have a different conformal dimension, and we should try and understand them. And the question is, well, is there any theory where this happens, obviously? The answer is yes, there is, well, many theories, but at least one that I have studied. So I'm going to tell you about that one. So the example I want to look at is a theory which is called the Li-Yang model. So the conformal field theory, the Li-Yang model, has two versions, the massive version and the conformal version, as usual. The conformal field theory is a minimal model, and it's actually the simplest, one of the simplest non-trivial minimal models, because it only has two fields in the spectrum. I'll show you in the next slide. But it is a non-unitary minimal model. It means, and that means in particular, that the central charge of this theory is negative, okay? All right, now this theory can be perturbed, and the result is a massive quantum field theory, integrable. Okay, so this is what I was saying about the fields. There are only two fields, 1 and phi. Because the theory is non-unitary, again, this field phi has a negative conformal dimension, -1/5. Okay, if you perturb this theory with the same field phi, you get a massive quantum field theory, which whose S matrix was famously found by Carl Musardo. And it's very simple. This is the scattering matrix. So this is a particle, this is a theory that has a single particle, interacts with itself, and the two-body scattering matrix is this. And this scattering matrix has a pole at 2 pi over 3, of course, and this can be interpreted as the formation of a bound state. So this particle can actually form a bound state with itself, okay? It's a bound state of itself in some sense. The CFT underlined this is non-unitary, so you would expect this will create some problems, but actually this S matrix is perfectly nice, perfectly well defined. So this is a model that is frequently studied in integrable quantum field theory. By the way, this S matrix is very similar to the one in Cinch-Gordon as well. Okay, so because there is a bound state, if you try to compute form factors of anything, you now have a bound state pole as well. So not just a kinematic pole. So the form factors are a little bit more complicated. So let me tell you something a bit more technical about the form factors. I mean, there's a reason for this, so you hopefully see it at the end. So suppose that I want to compute the form factors of twist field in this theory. Why not? So, okay, let's do that. We did that in this paper in 2015. If you follow what I explained about form factors last week, well, there is a minimal form factor you can construct. It has an exponential representation like this. But because you have this bound state in the S matrix, the form factor also has another pole. And this pole, you can introduce it, for example, by multiplying with a function like this. So this idea actually comes already from Samologikov that studied this theory for the operators. But for the twist field, it's kind of the same, almost the same. So you can think of this minimal solution to the two particle form factor equation like this. And as I wrote last week, you can then say, okay, the form factor of the twist field should look something like that. So it has the kinematic poles and it has the bound state pole hidden here. Okay. Now we already mentioned last week that this solution is, however, not the only solution that you can write. And this was even one of the poll questions that I asked you last week. And in fact, the most general solution that you can write is something like this at the bottom. So it looks very similar, but actually you can always add a term that's proportional to the minimal form factor, simply because the minimal form factor by construction satisfies all the equations. Okay. Now, the reason why we normally don't add that term is because if that term is there, in particular, the asymptotics for theta large of the form factor is changed. And that simple change, actually, in many cases, this is not allowed. For example, if you have C2 symmetry, you don't want to have that term in there. So there are usually enough constraints to get rid of it. But in the Lee-Yang model, there's no reason to get rid of that term. So you use that most general solution, okay? So suppose that I write that solution. Once I write this, okay, in fact, I have multiple solutions because I have this kappa here, which is a constant, an arbitrary constant. All of these functions are solutions of the form factor equation. So question is, what is this field? Oh, what twist field is this? How do I identify that? Well, I have some constraints that I can use. So one constraint was this momentum space clustering, decomposition property. So I expect that when theta is large, my two-particle form factor will become some constant. In fact, with these definitions I gave you, it becomes that constant, kappa. And clustering tells me that should be related to the one-particle form factor squared, properly normalized. So that gives me a constraint. And the other constraint is that I have a bound state residue equation. So I know that the residue of the pole of this form factor at the bound state, that should also be proportional to the one particle form factor, okay? By a constant, which in this model is actually this constant here. That's the residue of the pole of the S matrix, the square root of it. And it has an I. The fact that there is an I actually is connected to the non-unitary nature of the theory in some sense. Okay, so I have these two equations for F1, in fact. So if you combine these equations for the one particle form factor, you actually get two solutions. Okay, you get a quadratic equation and you get two possible solutions. So what you conclude then is that, okay, your form factor solutions for the twist field, they are not unique, but there seem to be two sensible solutions only that satisfy, if you want to satisfy these constraints here, in particular clustering. Still, you don't know what these solutions correspond to yet. So what operator is this? Is this the standard twist field? Is this something else? So you don't know that, but it's not hard to find out. And I'm coming to the conclusion of this. So what are these fields? Well, these are the one particle form factors here. Now remember that one thing I told you many, many times today is that the form factors of the twist field are 0 at n equals 1, should be. So if you look at that formula, you actually realize that this happens for O minus, for the minus sign, okay? It should happen at least, unless I made a typo somewhere. So so it looks like one of the solutions is indeed the form factor of T. And you would expect that because these are, after all, the twist field form factor equations. But then there's still the other field, and the other field doesn't have this property. So its form factor is not 0 at 1. So what could that mean? Well, what is it then? So if you compute the limit n to 1 of this form factor, you get a result, you get a number. And if you know a little bit of literature, you realize that that number is actually the one particle form factor of the field phi, so the fundamental field of Lee-Yang. Okay, remember there was this field that is present in the Lee-Yang theory. And actually this was computed by Samologikov in the 90s. So what does this suggest? Well, this suggests that there are actually two twist fields in this theory that you can define with the same twist property. One is the standard twist field T, and the other is a field that I'm going to call T phi with dots indicating normal ordering. So T phi is an example of what I have called previously a composite twist field. So it's a field that is kind of made out of two different fields. One is a twist field, the other is not a twist field. So in the next slide, I will tell you more precisely how you make sense of that composition. But if you think of this field as, I mean, in CFT at least, you can think of it as the leading field in the OP expansion of T with phi. So if you take T and you take phi in conformal field theory and you do an operator product expansion, the leading field in that expansion will be some sort of composite field like this. So this is one way you can interpret it, and you can make that a little bit more precise. So let me show you that. So remember this formula. So delta t was the conformal dimension of the standard twist field. I told you some time ago that there is other types of twist field that have a different dimension, and whose dimension is actually determined by something called the effective central charge instead of the central charge. So this effective central charge is a number that plays a role often in non-unitary conformal field theories. So you have theories where C is negative, but it turns out that if you subtract a certain quantity, the resulting, well, CF is actually positive. And this CF seems to govern the behavior of lots of quantities in non-unitary CFT and in perturbations thereof. So the dimension of this T phi is a dimension like this, depends on the dimension of phi, it depends on the original C. So this is a kind of field that actually, again, had been already identified in the context of studying orbifold conformal field theories, non-unitary conformal field theories. If you look at these dimensions here, you realize that if you are in a theory like Li-Yang, the dimension of the standard twist field is actually a negative number, which is usually something that is not very nice, whereas the dimension of T phi is a positive number, which is a little bit nicer. So T phi is the branch point twist field with the least positive dimension that we have in this theory. Okay. So how can you define this field a bit more precisely? So as I told you, the way these composite twist fields can be defined is in conformal field theory. That's the best way. And the proper definition is written here. So remember that we are in a replica theory. So actually, in a replica theory, there is no field phi per se. There is actually one field phi per copy. So actually, when I write T phi here, what I mean in the CFT is that I'm looking at the sum, well, at the OPE of T with each of the phi's on each of these copies. So J is the sum of copies from 1 to n. So I'm looking at the operator product expansion of this T of X with phi J of Y, normalized by some power, which has to do with the dimensions of these two fields, so it can be computed from conformal field theory. And then here there is some normalization with n, and this normalization can be calculated just by imposing conformal normalization of the two-point function. So what this means is that the two-point function of T phi in CFT goes like 1 over the distance to a power. So that 1 in there can be achieved if you define the T phi field in this way. So if you normalize it in this way in conformal field theory. Now, as usual, once you have this field in CFT, you normally think that when you perturb the CFT, this field will flow to some other field in the massive theory, and this is the T phi that we can study with form factors. So this is an example where the form factor equations somehow, without much input, immediately tell us that in this theory, it is natural to have two twist fields, which is quite a nice result. I quite like it, even if it's not very, very well known, I think. So this kind of composite twist fields between a twist field and a field that is not associated to a symmetry at all, they were studied. I think the first time we wrote them was in some paper where we were looking at actually trying to derive some mu-C theorem from entanglement, which we kind of have succeeded. And then my student Emanuele sort of looked at many kinds of fields of this type. And the reason why we were interested in them initially was that at some point we figured that we could define, I mean, one nice way to define an entanglement entropy in non-unitary conformal field theory and then extend it to massive theories would be to say that if your theory is non-unitary like Li-Yang, and therefore the two-point function of the standard twist field is not going like x raised to a positive power instead of a negative one, which would be the normal thing. One way to solve that problem in a way would be to replace that two-point function by a ratio of two-point functions of this type. So somehow it would be more natural to use this field T phi, which has a positive conformal dimension, than to use the original T. And in fact, if you use this replacement, then what you find is that entanglement entropy, for example, behaves just as usual. So it grows logarithmically and so on, but the central charge is replaced by the effective central charge instead. So you have a quantity that is still positive definite and has nice properties. So this is one of the reasons why we studied these fields initially in this paper. And there is now some evidence in lattice theory, so from doing numerics, that this kind of definition seems to work. Although there are also some people that dispute that this is a correct definition of entanglement. So this is not, there's still some discussion around this, but that doesn't take away the fact that these composite fields can be defined. So that's a different story. One way you can think of these correlators and of these fields in the context of entanglement is an updated picture of this Riemann surface, where at each branch point, now you also have an insertion of this field phi. Okay, so I'm almost done. This example gives you an idea of how the form factor program connects to the identification of operator content in integral quantum field theory. This is, of course, not a new problem. So people have, of course, asked the question, how many solutions are there to form factor equations? It is a deep question. And people have looked at it at least in model-specific situations. So Cardi and Musardo thought about it for the Ising model. Kubek, Musardo thought about it for Sinch-Gordon, and we thought about it for a different family of theories, these homogeneous and Gordon models. So this is an interesting question, and this work I'm describing tries to address it a little bit for twist fields. And an interesting extension of all of this is to think of a case when the field phi is also a twist field. So it's not completely neutral. And this is not what we did in this work I'm talking about. We always thought about fields that were neutral. But if they are not, then this composite field would not satisfy the same equations as the twist field, will satisfy some modified equations. And this is something I think I already mentioned, but has been studied recently by David and Pasquale in a recent paper. They call these fields symmetry resolved twist fields, and they seem to also have an application to compute a particular measure of entanglement. So I wanted to end with this also to suggest that there's still things to be discovered with twist fields. So for example, the symmetry resolved twist fields is quite a brand new thing. There's still many things to compute, and I think they can tell us quite a lot about entanglement in different settings, both at equilibrium and out of equilibrium. So I found a nice picture online that illustrates this, I think. I forgot this last line. So this symmetry resolved entanglement was defined here. I just wanted to end with a picture to say that the story goes on. And this is actually I think from a video game, I found this. But then I added for branch point twist fields. So hopefully I can come back and tell you more in the future, or you can tell me if you start working in this. Thank you.
Thank you, Olalla. I wish I clapped for everybody that
thank you.
we cannot do as usual. Thank you really a lot. I don't know if there are questions now, or we can just have a break and start a bit before the discussion section. I think will be the best thing to do.
Yeah, we can do that. So
so that maybe we start with your and not with the other. And
yeah, so I have to, I mean, the only constraint I have is that I have to leave at 15 minutes before 5 because
that's why.
But that's there's still a lot of time until that. I think it will be fine. So if you want to take 10 minutes or 15 minutes.
Yeah, 10 minutes. Let's make it 4 sharp so that.
4. Okay. Okay.
Andrea,
good.
you will chair the other session, no? Or
yes,
Jacopo?
Yes.
Andrea, okay, perfect.
Yeah.
I'm still around.
Okay.
Yeah. Okay.
I stop the recording.
See you soon, and thank you again.
Yeah.
Thank you, Olalla.
No Thanks.
You.
So see you.